In this tutorial I'm going to describe the oxidation of alcohols to the corresponding carbonyl compounds, in this case ethanol to the aldehyde ethanal. Now this is covered in AS chemistry, and, but I also go through this again with my year 13 students in preparation for teaching them the reverse process, which is reduction of a carbonyl compound to an alcohol. So there's the ethanol and the ethanal. In order to write a balanced equation, the simplest possible balanced equation, I need to put two hydrogens on this side because there are two fewer hydrogens in ethanal than in ethanol, so you can imagine it's these two hydrogens that have been removed. Notice I've put the two hydrogen atoms in square brackets. That's to indicate that I'm not specifying where they are going. For example, I'm not writing them as H2 because they certainly do not come off as a H2 molecule. Okay, so more on that later. Now, the way you're shown to write this reaction in the textbooks, and I'm sure you'll be shown at school, is to put an oxygen atom in square brackets. So that's to represent the oxidant that you're using, and that oxygen atom then combines with the two hydrogens to make a H2O molecule. So we've got H2, the two hydrogens removed from the ethanol, and the oxygen. And in most cases, when you're asked to write a balanced equation for the oxidation of an alcohol, this is what you would do, particularly in the exams. I'm going to look in a little bit more detail about what's going on here. So we've said that this is an oxidation reaction. And now the definition of oxidation is when a substance loses electrons. Now people will say to you, oh, this is oxidation because we're losing hydrogens. And that's perfectly true, but it's because the hydrogens contain electrons. So when you take a hydrogen atom away from ethanol, what you're really doing is removing an electron. If you think about what's inside a hydrogen atom, there's a H atom. It consists of one proton and one electron. There are no other protons or electrons, just one of each, no neutrons. So we can write H, just one hydrogen atom, is the same as a hydrogen ion, which is exactly the same as a proton, plus an electron. So if we go back to my earlier representation of this reaction, just get rid of that one and just show the two hydrogens coming off. And instead of showing two hydrogen atoms, I'm just going to write a proton and an electron for each hydrogen atom. So it's going to be plus 2 H plus 2 electrons. And now it's easy to see how the reaction fits the definition of oxidation. It's loss of electrons. It just so happens that the alcohol's also losing two H plus ions, but they're nothing really to do with the definition of oxidation. Oxidation is the loss of electrons. So in some cases, oxidation is the loss of only electrons. So for example, if we have the iron 2 plus ion, it can lose one electron to make the Fe3 plus. And that's quite easy to see that that's loss of electrons. But in organic chemistry, you often find the electrons are accompanied by protons. So overall, you've lost a hydrogen atom. So it's fine to say that oxidation is the loss of a hydrogen atom, but certainly not okay to say it's the loss of a proton, because there are no electrons in a proton. It's nothing to do with the proton. That would just be an acid-base type reaction if it's just the release of a proton. Okay. Now, by writing the hydrogen atoms as separate protons and electrons, we can consider what happens to them, where they go. Well, this one the electrons are used to reduce the oxidizing agent, which is acidified potassium dichromate 6, so K2Cr2O7. So the acid can be sulfuric acid or hydrochloric acid. This could be the sodium salt. It's the dichromate 6 ion that matters. But that takes the electrons and it gets reduced. I'll explain that in more detail in a moment. And you can think of the hydrogens as combining with the oxygen. If I now write my oxygen atom up here, then you can think of the two protons as combining with the oxygen to make H2O. So to do that, it would be 2H plus an oxide ion gives H2O. So you can think of that oxide ion as coming out of the dichromate 6, but we just write the oxygen there. The actual mechanism of this is very complicated indeed. It involves the formation of an ester between the dichromate and the ethanol. You certainly don't need to worry about that. But that's why we can represent this reaction in different ways, and each way we represent the reaction gives us a different perspective on it. But I like this because it shows that the electrons go to the metal, to the oxidants, and the protons, well, they're part company from the electrons. And so let's have a look at the potassium dichromate 6 then, how that's involved. So I'm just going to leave that reaction as it stands because that is a balanced half reaction. Half reactions show either oxidation or reduction. So if it's oxidation, the electrons are on the right hand side because the ethanol has lost electrons, but they don't tell us where the electrons go. So in our case the electrons are going to the dichromate 6 ion, but you could use a different oxidant. You could, for example, use manganate 7 and then the electrons would go to that one. So let's look in more detail at the dichromate 6. Potassium dichromate 6 then, K2Cr2O7. Remember, it has to be acidified. When that one dissolves in water, it dissociates into ions. Now, potassium ions, when dissolved in water, of course, are colourless. But the dichromate 6 ions, so that's Cr2O7 2- aqueous, they are responsible for the orange colour. So this is what you are seeing when you see this orange colour, and this is what you're using to oxidise the alcohol, but it's under acidified conditions. So let's have a look. How do the electrons reduce the dichromate 6 ion? I'm just going to construct a half equation to show that. Now here's the Cr2O7 2-. You just have to learn that that gets reduced to the chromium 3+ ion, Cr3+. And because there are 2 chromium atoms in the dichromate 6 ion, you make 2 of the chromium 3+ ions. And you also need to remember the colour changes. They often ask you in the exam questions, what would you observe? And you'd observe the colour changing from orange to green. Now let's have a quick review of the oxidation numbers in here. This is straightforward. Each chromium is in the +3 oxidation state. It's a simple ion, so the oxidation state is the same as the charge. This one, we have to apply the rules of working out the oxidation state. Oxygen is always -2 unless it's in peroxide, so we've got 7 of them. 1, 2, 3, 4, 5, 6, 7. So they come to -14. Although they add up to a total of -14, it would be incorrect to say the oxidation state, or number of oxygen, in the dichromate 6 ion is minus 14. It's not. Oxidation numbers refer always to just one atom, so we still say the oxidation number of oxygen in the dichromate 6 ion is minus 2. Okay. Now the sum of all the oxidation numbers must add up to the charge, and that is possible if both of the chromiums are plus 6, and that gives us plus 12. So plus 12 minus 14 gives us the minus 2 charge. Okay, so I'm just going to write the only the chromiums, because the oxygens are not going to change oxidation state in this reaction. So we've got chromium going from plus 6 to plus 3. That is a reduction reaction. Reduction is always when the oxidation number becomes less positive, and oxidation is when the oxidation number becomes more positive. That's the way to remember it. Oxidation is when the oxidation number becomes more positive. It's moving in the positive direction. Reduction is when the oxidation number becomes less positive. Just remember that, and everything else will fit into place. So this is more positive than this, so this is more oxidized than this. If we're going from plus 6 to plus 3, we're becoming less positive, so it's a reduction reaction. And changes in oxidation number correspond exactly to numbers of electrons. So to go from plus 6 to plus 3, we have to add 3 electrons, plus 3 electrons. But we've got 2 chromiums doing this, so altogether we've got to add 3 electrons. Okay. This business of the oxidation numbers, we can apply it to organic molecules as well, even though they usually don't tell you about this at school, but it's particularly useful for organic substances, because if you don't have ions, it's hard to see where the electrons are moving. So I'll just do the ethanol just to show you this, and make a little bit of space here. Right, in ethanol, oxygen is minus 2, unless it's a peroxide. Hydrogen is plus 1, plus 1, plus 1, plus 1, plus 1, and plus 1. So if we've got 6 positives and 2 minuses, that gives us a total of plus 4. So it means that each carbon must be minus 2. So carbon is in the oxidation state minus 2. That lot adds up to 0 because obviously there's no charge on ethanol. Do the same thing over here. We've got 1, 2, 3, 4 pluses and 2 minuses. So the 2 carbons have got to balance the minus 2. So each carbon is minus 1, minus 1. So the oxidation number of carbon in here is going from minus 2 to minus 1, and it's happening for each of the carbons. So that's becoming less positive. Excuse me, that's becoming more positive. It's going in a positive direction. Minus 2 up to minus 1 is moving towards positive, so it's an oxidation. And to get from minus 2 to minus 1, you need to add 1 electron, but we've got 2 of the carbons doing that, so that's why we have the 2 electrons here. So you can see how if you approach your chemical reaction from different perspectives, different angles, it all really does fit together. It's very consistent. So let's press on with this half equation over here. So the procedure then, when you're constructing a half equation, is first of all to assign the oxidation numbers of the species on each side of the equation to see who's being oxidized and who's being reduced, and then you balance the oxidation number by adding the appropriate number of electrons, to the left if it's a reduction and to the right if it's an oxidation. Okay, so that's representing the 6 electrons we need to remove to reduce 2 chromiums in the plus state to 2 in the 3. The next step is to look at the oxygens, and we've got 7 oxygens on this side, none on this side, so we balance the oxygens by adding H2O molecules. And so to get 7 oxygens we need 7 H2O molecules. And then we look at the hydrogens, which we've introduced by adding 7 waters. So we've got 14 hydrogens on the right. We balance those by adding protons on the left. So I have to put 14 protons. Did I say 7 hydrogens? There are 14 hydrogens there, obviously in 7 H2Os, so we need 7 protons on that side. And that is our half reaction for the reduction of dichromate 6 to chromium 3. And this is a half reaction for the oxidation of ethanol to ethanal. Whenever you've written a half reaction, always check it. First of all, check for the atoms, and then check for the charges. So we're checking the balancing, yeah? Always do that, and that way you'll never get one of these wrong. What you certainly shouldn't be doing is trying to memorize these half equations. You should learn how to work them out each time. So quite simply, we have 2 chromiums, 2 chromiums, 7 oxygens, 7 oxygens, 14 hydrogens, 14 hydrogens, balanced in the atoms. And we look at the charges. We've got 2 chromiums, each is 3 plus, so they come to 6 plus. We've got 14 pluses here, but we've got 8 minuses altogether, 6 electrons, and the 2 minus here. So again, we've got 6 plus on that side. So that's balanced. Okay. So what we've got to do now is to write an overall reaction or equation to show the oxidation of ethanol by dichromate 6. Is we've got to match the number of electrons that the dichromate 6 needs, which is 6, with the number of electrons the ethanol is losing, which is only 2. So we're trying to match the seller with the buyer. It's a supply and demand. At the moment there's a mismatch. So for one dichromate 6 to be reduced, we need to oxidize, in fact, 3 of the ethanols. So I'm going to write that underneath. So if I oxidize 3 ethanols, CH3OH, and they're going to give me 3 molecules of ethanol. They're going to give me 6 protons and 6 electrons. And now the number of electrons lost by the ethanol matches the number of electrons required by the dichromate 6. So I can just add those together to give one overall reaction. But before doing so, it's possible to cancel out the electrons because we've got the same number on each side, just as you would do in maths when you cancel both sides of the equation. We can also balance down some protons. If we take away 6 from each side, and you've got none there, and you have 8 left on here. So now I will combine the equations. So I have 3 ethanol molecules, I'll put the dichromate 6 in orange to remind you of its colour, because as I said earlier, it's very important to remember this. Cr2O72 minus. I'll also put the acid protons in red, because you have to remember that it's acidified. And now you can see why it has to be done under acid conditions. You need 8 protons, and then that gives me 2 chromium 3 ions, 2 lots of Cr3 plus. It gives me 3 ethanol molecules, and 7 water molecules. And again, always check. You need never get one of these wrong, because you can always check the balancing. And the procedure is check the atoms and then check the charges. I'll start off with the carbons. One ethanol molecule has got 2 carbons in. We've got 3 of them, that's 6. Similarly for the ethanol, we've got 6 carbons in 3 ethanol molecules. One ethanol molecule has 6 hydrogens in it. We've got 3 of them, that's 18 hydrogens there. 8 hydrogens here, that's 26. Now each ethanol molecule has got 4 hydrogens in. 3 of those gives 12, plus 14 gives 26. 2 chromiums, that's easy. We've done no, we haven't done the oxygens, have we? We've got 7 oxygens in the dichromate 6, plus 3 from the 3 ethanol gives 10 oxygens. Here we've got 7 oxygens in the 7 water molecules, plus 3 makes 10. So we can say that it's charged, that the atoms are balanced. And then if I look at the overall charge on both sides, it should be the same. So I've got a total of 6 plus on this side, 2 lots of 3 plus. Here I've got, what have I done here? I've put that as a, excuse me, that should be a minus. So we've got a total of 8 pluses and 2 minuses gives 6 plus. So you've just seen there how you need never get these wrong. We all make mistakes, but if you check your charges and your atoms, then you will spot any mistake. So don't try and memorise these equations, just learn how to work them out. We've just seen how ethanol is oxidised by acidified potassium dichromate 6 to give ethanol, which I have at the top here. If you allow the reaction to continue, the ethanol becomes oxidised to a carboxylic acid. But before I show you that reaction, it's helpful to compare the different categories or families of alcohols, because they behave differently when you try to oxidise them. Ethanol is an example of a primary alcohol. I'll just write it like that, but you shouldn't use abbreviations in the exams. You should write it's a primary alcohol, spell it out. The way I identify that as a primary alcohol is I look at the alcohol group. There's the carbon, the oxygen and the hydrogen, and I look at the carbon atoms attached to that carbon. So that carbon has got one other carbon attached to it, so that's why it's a primary alcohol. If we look at the next one, here is the alcohol group, and then the carbon of the alcohol group is bonded to this carbon and this carbon, so that means this one is a secondary alcohol. It's propane-2-ol, of course. And then if we look at this one, here is the alcohol group with its carbon, and we have 1, 2, 3 carbons covalently bonded to the carbon of the alcohol group, so that makes that one a tertiary alcohol. Okay. Now, seen already that if you oxidise a primary alcohol, you get an aldehyde. Ethanol is an example of an aldehyde. This is the aldehyde group. It's when you get a C double bond O, and it's at the end of a chain. So on one side of the carbon you've got a hydrogen atom, on the other side you have another carbon. So that would be an aldehyde. We bring about the same oxidation with a secondary alcohol. Then this time we generate a ketone. So here is the carbon of the alcohol group. We're going to lose this hydrogen and this hydrogen. So the oxygen, the double bond to the oxygen comes down here and then onto the other carbon. So we've got the same C double bond O, but we don't have a hydrogen attached. It's got a carbon on both sides, so that makes it into a ketone. So ketones and aldehydes, they're both carbonyl compounds because they've both got the C double bond O, but aldehydes are at the end of the carbon chain, whereas ketones are within the molecule. And if we look at the tertiary alcohol, well, using the reagents that we have at A-level chemistry, they're not oxidized. Not oxidized by acidified potassium dichromate 6. There are other reagents you could use to oxidize them, but at A-level, as far as we're concerned, tertiary alcohols are not oxidized. Secondary alcohols are oxidized to give ketones, and primary alcohols are oxidized to give aldehydes. Now, once you've oxidized a secondary alcohol to a ketone, it doesn't undergo any further oxidation. So, no further oxidation. So if you've got a secondary alcohol in a flask and you've got in there some acidified dichromate 6, you can reflux it for as long as you like, and you know that you will make only the ketone. Okay, but with a primary alcohol, it's very different. The aldehyde that you form is oxidized further to give a carboxylic acid. So here is our aldehyde. In this case it's ethanol. And I'm going to show it being oxidized again by showing the oxidant as just an oxygen atom that's coming along. So it would be the same as what we have over here. I want to balance the equations now. So in this case, the two hydrogens that come off form H2O with the oxidant. But in the case of the aldehyde being oxidized, we don't actually remove any hydrogens. The oxygen becomes inserted, if you like, to make a carboxylic acid. So this oxygen, the double bond is there. We come down to here and we're putting an oxygen atom in here, and we have the hydrogen here. So that's now a carboxylic acid. In this particular case, of course, it's called ethanoic acid. This is based on ethane, ethanoic acid. Now, if you're writing equations for these reactions, you've got to think about whether you're showing the oxidation of ethanol just to the aldehyde, or all the way to the carboxylic acid. I've written here balanced equations for the oxidation of ethanol, a primary alcohol, to ethanol, an aldehyde, and propantuol, a secondary alcohol, to a ketone, propanone. Now, when you're asked to write balanced equations for the oxidation of alcohols, 9 times out of 10 this is what's expected. You'll get that from the mark schemes in the exams. So you just show the oxidant as an oxygen atom. I've shown it in red. But you must balance the hydrogens, and so when you're oxidizing an alcohol to a carbonyl compound, you always form a molecule of water because you're removing 2 hydrogens, which I showed you earlier using the structural formulae. Now, in the case of a secondary alcohol, once you form the ketone, there's no further oxidation, so you can just reflux that, in other words, boil it and condense it for as long as you want to make sure all of the alcohol is oxidized to the ketone. But in the case of a primary alcohol, you if you continue allowing the oxidant to react, then it will oxidize the aldehyde, ethanal, to a carboxylic acid. And I've shown you that in the full structural formula, but let me just show you how you'd write a simple balanced equation for that. So it would be CH3CHO, and it would give the carboxylic acid, ethanoic acid, CH3CO, and I'll put that as one of the oxygens in red because it's coming from the oxidant, just to remind you. But notice there's no water produced in this reaction. So what I've got there is I've got the stepwise oxidation of ethanol, first of all to the aldehyde and then through to the carboxylic acid. But sometimes you're asked to write the reaction for the oxidation of the alcohol all the way through to the carboxylic acid in one step. So really you've got to combine these equations. What I can do is, if I cancel that out and cancel that out, then you can see that you need a molecule of ethanol, but this time you have to show two oxygen atoms. And you make your ethanoic acid going directly to the carboxylic acid. So one of the oxygens is part of the carboxylic acid, and the other combines with the two hydrogens taken from the alcohol in the first part of the reaction. So that will be an overall reaction. Again, I can apply oxidation numbers to this. If you remember that the oxidation number of carbon in ethanol was -2. In the ethanal it was -1. In ethanoic acid, what we have now is we've got +4, so we've got 3 hydrogens there and 1 there, so that's +4. We've got -2 and -2 for the 2 oxygens, so that lot adds to 0. So the oxidation number of the 2 carbons, they're each oxidation 0. So again, it fits our definition of oxidation, because the oxidation number is becoming more positive. Going from -2 to 0 is in the positive direction. Now here, of course, I've shown it in one big step. So to get from -2 to 0, you need 2 electrons for that one. You remove 2 electrons, yeah, -2 electrons, and you remove 2 electrons from that one. So that overall is a 4 electron oxidation. Here you're going, it's a -2 electrons, and here it's -2 electrons, because here you're going from -1 and -1 to 0. Okay, so just watch that when you're writing these equations. Make sure you understand whether you're asked to write the equation for the primary alcohol just to the aldehyde or all the way to the carboxylic acid, and remember that you only produce a water molecule when it's the former, and you'll be fine.